Welcome, everyone, to another deep dive. We're here to take complex information, dense research, interesting data, and really distill it down into those key insights, those aha moments. We want you to walk away feeling genuinely connected to the hidden patterns in the world of knowledge. And today, we've got something special lined up, particularly for you number theory students listening in. As part of our ongoing exploration of the online encyclopedia of integer sequences, the OES, an incredible resource, really. Our sequence today is A00258. Now, the formal OEIS definition might look a little daunting at first. It says expansion of EGF XPX11.
Right. That's an iterated exponential generating function. It's quite elegant, actually.
Like a mathematical fingerprint, encoding the whole sequence.
Exactly. It often reveals a lot about the underlying structure, like its DNA.
And the sequence itself starts, let's see, 1, 1, 3, 12, 60, 358, 2, 4, 71. It climbs pretty quickly.
It certainly does. That rapid growth is often a sign of combinatorial complexity.
So the big question is, what are these numbers actually counting? What structures are hidden behind this formula and these terms?
Well, that generating function, the XP, X by XP, those nested exponentials, they're the first big clue. It screams layers. And this isn't a new sequence, by the way. It has older codes, M2932 and M11178. It's been around.
Ah, so it has some history.
Definitely. And Neil Sloan himself, the founder of OEIS, is listed as the author. It's foundational.
And still relevant, I see. The entry was updated very recently, June 23, 2025.
That's right. The mathematical community keeps refining and adding to these entries. It's a living encyclopedia.
Okay, so beyond that elegant formula, what do these numbers mean? What kind of, tangible things are we counting here? What problems does A00258 help us tackle?
Right, let's get into the combinatorics. The most intuitive way to think about AN is this. It's the number of ways to partition the set 1, 2x.
Okay, standard partitions.
But then you take each block, each cell from that first partition, and you partition it again into subcells. So it's a partition of a partition.
Ah, okay, a two-stage process. Can you give us an example, maybe for a small n?
Sure, let's take N2. The set is 1, 2, first stage. We partition 1, 2. Two ways, either 1, 2, or 1, 2.
Got it. Two separate elements or one block with both.
Exactly. Now, stage 2, for 1, 2, the cell 1 can only be subpartitioned as 1. Same for 2, it becomes 2. So that gives one outcome.
Okay, only one way there.
Now, for the other initial partition, 1, 2, we need to partition this single block. We can keep it as one subcell, 1, 2, or split it into two subcells, 1.
So two ways for that one.
Correct. That gives us two outcomes, 1, 2.
Just adding them up. One way from the first case, two from the second. That's three total ways for N2.
Precisely. And if you look at the sequence, 1, 1, 3, A2 is indeed 3. It matches perfectly.
It really clicks when you see the example. Does that partition of a partition idea sometimes trip students up, or is it usually clear once they work through it?
That's a fair question. I think the visualization can be the tricky part initially, but the example usually helps, and there's a nice visual way to think about it, too.
Wow.
Christian Bauer pointed this out in '98. He described AN as the number of three-level labeled rooted trees with N leaves.
Okay, three-level trees. How does that work?
Imagine a root node at the top, level 1. Its children are level 2, and their children are the leaves at level 3. Labeled just means the N leaves are distinct, like our set elements 1.
So the structure of the tree mirrors the layered partitioning.
Exactly.
Yeah.
The branching represents the partitioning choices at each level. It provides a nice mental picture for that layered structure.
That's helpful. Now, I saw another interpretation mentioned involving pairs of partitions where one is finer than the other.
Ah, yes. That's A. Joseph Kennedy's contribution from 2006. A00258 counts pairs of set partitions, let's call them D and D, of the set 1, Phillies, with the condition that D is finer than D.
Finer than D. What does that mean precisely in terms of partitions?
It means that every block, every subset in partition D is completely contained within some block of partition D prime. Think of D as breaking the set down into smaller pieces than D prime or refining it.
Okay, like is finer than D.
Exactly. And Kennedy actually took this further, linking A0000258 to something much more abstract, the dimensions of class partition algebras.
Class partition algebras.
Yeah.
That sounds deep.
It is. We probably won't dive fully into the definition here, but the key idea is that these are algebraic structures important in representation theory. They relate to symmetries. specifically the centralizers of wreath products.
Wow.
And A00258, these simple-looking numbers, they actually give you the dimension, sort of the size or complexity of these important algebraic objects.
Wow. So the number of ways to do these layered partitions tells you the scale of some abstract algebraic structure.
That's the fascinating connection, yes. It shows how basic counting principles can underpin really sophisticated algebra.
That's quite a jump.
Ah.
Okay, so for students wanting to, actually calculate these numbers or understand the mechanics, what are the key formulas, the relationships you reveal?
Absolutely. The most fundamental formula here from Detlef Pauli in 2002 is really elegant. It connects A00258 directly to two very famous sequences.
Oh, which ones?
The formula is AN is the sum from KO to N of Stirling to N K times Bell K.
Stirling numbers of the second kind and Bell numbers.
Right, okay.
Foundational stuff.
Exactly. Let's quickly recap those. Bell numbers, that's A00001 nonde, count the total number of ways to partition a set of size K.
Right, all possible partitions for K items.
And Stirling numbers of the second kind, Stirling to NK, count the ways to partition a set of N elements into exactly K non-empty blocks.
Okay, so Stirling specifies the number of blocks.
Precisely. So look at the formula again. Sum Stirling to NK. You're summing over K, the number of blocks in the first partition. Stirling to NK counts the ways to get K blocks from your N elements. Then for each of those ways, you multiply by Bell, which is the number of ways to structure or partition those K blocks themselves in the second stage.
Ah, it perfectly mirrors the partition of a partition idea. The Stirling number handles the first partition into K blocks, and the Bell number handles the partitioning of those K blocks.
You've got it. It's a beautiful combinatorial identity that directly encodes that two-level structure.
That really clarifies things. Are there other interesting formulas or representations?
Yes, there are. Ilya Gutkovsky gave a generating function in 2019 that also explicitly involves Bell numbers. The sum J, Bell J, XJ, product K, 1.J, 1KX. Another way to see the Bell numbers at the core.
Still centered on Bell numbers.
And Carol Penson pointed out a Dubinsky-type formula back in 2003. These usually involve infinite series and connect to analysis and probability. It hints at deeper connections, often seen with sequences involving exponentials.
So ties to analysis too.
Right. And of course, for practical work, there are implementations available in common software like Maple, Mathematica, Maxima, Magma. Mathematicians can compute and explore these numbers relatively easily now.
It's clearly a sequence with deep roots in combinatorics. But you hinted earlier pops up elsewhere. Beyond partitions and trees, where else does A00258 make an appearance? This is where it gets really surprising, maybe.
This is where the sheer breadth becomes apparent. It's not just confined to its combinatorial origins. For instance, it appears in work on formal power series, dating back to Ulrich Sadler in 1994.
Okay, algebraic structures.
And more recently in things like combinatorial Hopf algebras, work by Aboud and others in 2014, and even Brouwer and Jones tied monoids, studied by Accardi et al. In 2021. These are advanced algebraic frameworks, and A00258 plays a role in understanding their structure.
Up algebras, monoids, still in the realm of algebra and structure.
True, but then it takes a rather unexpected leap. It shows up in quantum physics and statistical mechanics.
Quantum physics? How?
Through concepts like Bose normal ordering, how you arrange quantum particle operators explored by Blasiak and colleagues using substitutions and Sheffer polynomials in 2005, and also in hierarchical Dubinsky-type relations, work by Penson et al., again in 2003, connecting these counting numbers to hierarchies in quantum systems.
So the way we count layered partitions has echoes in how quantum systems are organized.
It seems so. The underlying mathematical patterns resonate across these fields. It's quite remarkable.
That is remarkable. Any other surprising connections?
Well, it even reaches into theoretical computer science. Hogg and Huberman mentioned it way back in 1985 in their study of attractors on finite sets, relating to the dynamics of computing structures, how patterns settle in complex systems.
Computing dynamics, too.
And fittingly, Neil Sloan himself, with Thomas Weider, wrote about the number of hierarchical orderings in 2003, tying back nicely to that tree interpretation we discussed earlier.
It's like this sequence is a thread connecting combinatorics, algebra, physics, computer science.
That's a great way to put it. What's truly fascinating is seeing how a sequence defined by something quite fundamental, counting layered arrangements, finds relevance and application across such diverse domains. It really highlights the interconnectedness of mathematical ideas. Patterns in one area often unlock understanding in another, sometimes very unexpectedly.
What an incredible tour of A00258. We started with that a compact but potent generating function and saw the sequence grow rapidly. Then we unpacked what it counts. These multi-level partitions, three-level rooted trees, pairs of partitions related by refinement, even connecting to the dimensions of class partition algebras. We saw its beautiful connection to the core building blocks, Bell numbers and Stirling numbers of the second kind, through that key recurrence relation.
A very revealing formula. And finally, explored its surprising reach, formal power series, Hopf algebras, yes, but then quantum physics, boson ordering, computational dynamics. It's truly widespread. All from a sequence the OEIS simply tags as non-easy nice.
Yes, those key words can sometimes undersell the depth. Nice certainly applies, but easy perhaps belies the rich web of connections it holds.
It really does.
And this brings up, I think, a really interesting point for everyone listening, especially those deep in number theory studies. Sequences like A00258 aren't just isolated curiosities. They function as bridges, mathematical bridges connecting different areas. So the provocative thought might be, what other seemingly simple sequences in the OEIS are holding keys? Keys to linking areas of maths you thought were separate, or maybe even keys to building new models for complex systems out there in the real world.
That's a great challenge.
So dive into the OEIS yourself. Use A00258 as maybe a gateway. Explore the links, follow the references, and see where these numbers take you. You might uncover some amazing connections.
Fantastic advice. A perfect place to end our deep dive for today. Thank you so much for guiding us through the fascinating world of A0000258. And thank you all for joining us. Keep exploring those connections, keep asking questions, and we'll catch you on the next deep dive.